MOSFET is field effect transistor made of both structure, and it has source and drain as the body part. This is the example with the N-type body. The source and drain's polarity is opposite to the body's polarity, so in this example, source and drain is N-type heavily doped semiconductor. When this structure gets into the inversion region, the mobile carrier's electrons will be accumulated at the interface between the gate dielectric and body. These mobile carriers will make a channel between source and drain. With this channel, mobile carriers at the source can easily move to the drain, and these mobile carriers will make a current. These two graphs are about the characteristic between the drain current and drain bias, and drain current with the gate bias. First, with the drain bias, the drain current increase linear before the specific part, but it keeps constant after this point. So we call this part linear region, and the part after the point called saturation region. And with this graph, we can know that the current occurs after the gate bias getting bigger than the threshold voltage. This is the formula about the drain current with the graph with the drain bias. The upper one is about the linear region, and the lower one is about the saturation region. In this formula, there are many components, but the components here, the width and length of the channel, mobile carrier's mobility, capacitance of the gate dielectrics, these components will be fixed when we make the device. But these other components, the gate bias and the drain bias, can be easily changed by the condition. This is the mobile carrier electrons concentration at the surface, and in this formula there's a part with the difference between the conduction band and Fermi level, and this component will be determined by the gate bias. If the gate bias getting bigger than before, the gap between the conduction band and Fermi level will be smaller than before. But the polarity of this component is negative, so the total amount of the electrons concentration will be bigger than before. As electrons carrier concentration getting bigger than before, the potential of p-type channel will be lower than before. So the electrons from the n-type source can easily move to the channel. This mobile carrier's movement will make the current, but if the drain bias is 0, the current cannot be generated. The drain part and the source part is namely the n-type, heavily doped n-type semiconductor. So the level of the energy band of each will be same. So if there's no bias at the drain part, the electrons from the source cannot move to the drain part. So we should make a positive drain bias at the drain part, so make a difference between these two different energy level to make the electrons from the source can easily move to the drain part. As a result, the drain current will be generated when the gate bias and drain bias has both huge value. But also it can be changed by the property of the devices. At the first graph, the threshold voltage value is bigger than 0, so at the point of the gate bias is 0, there's no current generated. We call this kind of device enhancement type device. But at the second graph, the value of the threshold voltage is negative, so at the point of the gate bias is 0, the current already generated. We call this type of device depletion device. This is about the MOSFET, but it also applies to the pipette.